Imagine this moment. The last generation standing beneath a darkening sky, watching the final ship rise from Earth's surface on a pillar of fire. It climbs through ash-laden clouds, engines roaring defiance against gravity, carrying humanity's chosen few toward a distant red world we've called our backup plan. Below, continents smolder. Oceans churn with unfamiliar tides. The atmosphere itself has become a stranger. And in this moment, as the ship's light fades into the cosmic dark, a question settles over those left behind. What if the dream of leaving was the very thing that stopped us from staying? Tonight, we explore a possibility that might seem impossible at first. That the backup planet plan, championed by brilliant minds, funded by vast fortunes, celebrated in films and dreams and midnight conversations, might not be our salvation. It might be the most dangerous fantasy our species has ever embraced. This isn't a story about whether we can reach Mars or terraform distant worlds. It's about what happens to us psychologically, culturally, morally, when we believe we can. It's about the subtle shift that occurs in human consciousness when Earth stops being our only home and becomes merely our first home. When survival stops being about preservation and becomes about escape. Across the darkness of our collective imagination, a vision has taken hold. Backup Earth. Plan B. A second chance written in the dust of Mars or beneath the ice of Europa. It sounds like hope. It feels like progress. The greatest minds of our generation pour resources into making it real, and we watch with wonder as rockets land themselves, as rovers traverse alien soil, as blueprints emerge for cities beneath foreign skies. But here, in the quiet space between ambition and consequence, we must ask an uncomfortable question. What if this dream, beautiful as it is teaching us the wrong lesson? What if the mere belief in a backup planet is making us less likely to survive on the one we have? The paradox is elegant and unsettling. The same technological optimism that could theoretically save us by spreading humanity across worlds might actually doom us by making Earth's problems feel temporary, solvable later, or simply someone else's burden to bear. When extinction feels reversible, when planetary destruction comes with an escape clause, human behavior changes in ways we barely notice until it's too late. Tonight, we'll journey through physics that cares nothing for our dreams, biology that evolved for one world only, and psychology that bends toward comfortable illusions. We'll trace the origins of the backup planet idea, not to mock it, but to understand how something so inspiring became so widespread. We'll stand on hostile worlds and feel what uninhabitable truly means, not as a challenge to overcome, but as a reality to respect. We'll examine what happens to the human body in space, not over days or weeks, but across the years and generations required to establish new worlds. We'll calculate the actual resources needed, not in inspirational terms, but in raw numbers that reveal uncomfortable truths. And we'll explore something perhaps more important than physics or biology, the human tendency toward escapism, our deep need to believe that when things get bad enough, somewhere else awaits. This investigation will take us through territory that might feel unfamiliar. We'll consider moral hazards, the way backup plans change our relationship with risk. We'll acknowledge what humans are actually remarkably good at: adapting, repairing, and restoring when we choose to. And we'll imagine a different vision entirely, one where space exploration exists not as an escape route, but as an expansion of consciousness, where we reach for other worlds not because we've failed this one, but because we've succeeded in cherishing it. By the time our journey ends, the stars will look different to you. not less beautiful, perhaps more so, but different. The backup planet dream will reveal itself not as destiny, but as choice. And in that revelation lies something more powerful than any rocket. The recognition that we are not trapped passengers on a dying world, but conscious architects of the only home we've ever truly known. If these questions intrigue you, if you find yourself drawn to explorations that challenge comfortable assumptions, I invite you to join this journey. And I'm curious, where are you right now as you watch this? What time is it in your part of the world? Comment below and let me know. There's something profound about knowing we're scattered across this one planet, sharing these thoughts across time zones, all looking up at the same stars from different angles. Now, let us begin. Let's trace this dream back to its origins and discover how the idea of leaving Earth became humanity's most seductive lullaby. The dream of a second world did not begin with rockets or billionaires. It began in the quiet pages of novels, in the imaginations of writers who gazed at the night sky and wondered what humanity might become if we could leave this cradle behind. H.G. Wells imagined Martians invading Earth in 1898, yet the deeper question lingered beneath his prose. Could we one day go to them? Could we become the travellers, the pioneers, the refugees seeking shelter on distant shores? Science fiction gave us the language of exodus long before we had the technology. Arthur C. Clarke, Isaac Asimov, Robert Heinlein. These architects of imagination built entire civilizations on the surfaces of Mars, Venus, and worlds we had never seen. In their stories, humanity did not merely visit other planets. We transformed them, we made them home. The backup planet was not yet a plan. It was a vision, a possibility suspended in the realm of what if. Then came the space age. With it, the dream shifted from fiction to engineering. We reached the moon. We sent probes to Mars. Suddenly, other worlds were not just stories. They were destinations with coordinates, atmospheric readings, and soil samples. The impossible was becoming merely difficult. And difficulty, as history has shown, is something humans are remarkably skilled at overcoming. But the true transformation of the backup planet idea came not from scientists or astronauts. It came from entrepreneurs. In the early 21st century, a new generation of visionaries emerged, not from government agencies, but from Silicon Valley. Elon Musk stood before audiences and declared that humanity must become a multi-planetary species. Jeff Bezos spoke of moving heavy industry off Earth, preserving our homeworld as a pristine garden while billions live and work in orbital colonies. These were not abstract musings. They were accompanied by rocket launches, spacecraft prototypes, and multi-billion-dollar investments. Musk, in particular, crystallized the backup planet narrative with a clarity that captured imaginations worldwide. Mars, he argued, was not just a destination for exploration, it was insurance against extinction. Asteroid impacts, nuclear war, climate catastrophe, pandemics, the list of existential threats is long and sobering. A self-sustaining city on Mars, he proposed, would ensure that consciousness, that humanity itself, would survive even if Earth did not. The rhetoric was powerful because it tapped into something primal, the survival instinct, the desire to protect not just ourselves, but the entire story of human civilization. There is something genuinely inspiring about this vision. The idea of humans as a multi-planetary species elevates us beyond the boundaries of our origins. It suggests we are not bound by the accidents of our evolutionary history, confined forever to this single blue sphere. It whispers that we can become something more, explorers not just of continents and oceans, but of worlds and star systems. This aspiration resonates across cultures and generations. It speaks to the explorer within us, the part that once crossed oceans in wooden ships, not knowing what lay beyond the horizon. And there is undeniable psychological comfort in the concept of a plan B, knowing that humanity has options, that we are working toward a future where our existence does not depend on a single fragile planet, offers reassurance in uncertain times. Climate models grow more alarming, political tensions simmer. The backup planet becomes not just a dream, but a source of hope, a promise that we are not trapped, that we have somewhere to go if things become unbearable here. Yet beneath this narrative runs a deeper current, one rooted in legitimate scientific curiosity. The same minds proposing backup planets are also those who genuinely wonder, what is out there? Could life exist beneath Europa's ice? What secrets lie in the soil of Mars? The drive to explore is woven into our DNA, not merely as escapism, but as inquiry. We seek to understand our cosmic context, to trace the origins of our solar system, to answer fundamental questions about existence itself. It is important, then, to distinguish between two different impulses. There is exploration for knowledge, the pure wonder of discovery that has always pushed humanity to investigate the unknown. And then there is escape planning, the strategic calculation that treats other planets not as subjects of study but as emergency exits, as lifeboats waiting in the cosmic dark. The backup planet idea sits at the intersection of both. It is born from genuine curiosity and technological ambition, yet it is sustained by something else entirely, the haunting suspicion that we may need it, that Earth, for all its beauty and abundance, may not be enough, that we as a species may require a cosmic safety net. And so the dream persists, carried forward by visionaries and engineers, fueled by capital and code, echoing across social media and conference stages. The backup planet is no longer just fiction. It is a goal, a mission, a plan etched in mission statements and 5-year projections. But is it real? And more importantly, is it possible? Before we dream of stepping foot on distant worlds, we must first reckon with the mathematics of distance. The cosmos does not yield to human ambition. It operates according to laws written long before our species looked up at the stars. And those laws tell us something humbling. Space is not just big. It is incomprehensibly, brutally vast. Mars, our nearest planetary neighbour that holds even a whisper of possibility, sits an average of 140 million miles from Earth. At its closest approach, during what astronomers call opposition, that distance shrinks to about 33.9 million miles. Even then, the journey is measured not in days or weeks, but in months. With current propulsion technology, a spacecraft carrying humans to Mars would take between 6 to 9 months, one way. This is not a voyage. It is an endurance test, conducted in a metal cylinder hurtling through the void at tens of thousands of miles per hour. To understand why this journey takes so long, we must understand the fundamental challenge of space travel, the rocket equation. Formulated by Russian scientist Konstantin Tsiolkovsky in 1897, this elegant mathematical relationship reveals a harsh truth. Every kilogram of payload requires fuel, but that fuel also has mass, which requires more fuel to move, which requires even more fuel to lift. The equation grows exponentially, creating what engineers call the tyranny of the rocket. To carry more supplies means carrying exponentially more fuel, which quickly becomes physically and economically impossible. This is why current spacecraft are small, cramped, and carry only the bare minimum for survival. The International Space Station, humanity's most advanced orbital outpost, required more than 40 separate launches to assemble. Moving even a modest settlement's worth of equipment and people to Mars would require hundreds, perhaps thousands of launches, each one burning through resources, time, and the narrow windows when planetary alignments make the journey possible. But Mars is just the beginning. Beyond the red planet, the distances cease to be numbers we can meaningfully grasp. They become abstractions, stretching our comprehension of time itself. Jupiter, with all its majesty and gravitational potential, lies between 365 and 601 million miles from Earth, depending on orbital positions. Reaching it takes years. The Juno spacecraft required 5 years to arrive. Europa Clipper, NASA's upcoming mission to Jupiter's icy moon, will take approximately 6 years. These are not quick reconnaissance missions. They are commitments that span presidential administrations, that outlast the careers of the engineers who launch them. Saturn, that golden giant wrapped in its impossible rings, sits nearly 900 million miles away at its closest. The journey there requires 7 years or more, even with gravity assists from other planets. Cassini, which gave us our most intimate portraits of Saturn, launched in 1997 and arrived in 2004. An entire childhood passes in the time it takes to reach Saturn's orbit. And these are still our neighbours, relatively speaking. Uranus lies 1.7 billion miles away. Neptune, nearly 3 billion. Voyager 2, travelling at over 34,000 miles per hour, took 12 years to reach Neptune. 12 years of silence and darkness, crossing a distance so great that radio signals from the spacecraft took over 4 hours to reach Earth, travelling at the speed of light itself. This is the brutal geometry of the solar system. Distance is not a barrier we can simply overcome with better engines or stronger will. It is woven into the fabric of orbital mechanics, into the gravitational dance of planets that has unfolded for billions of years. Current propulsion systems rely primarily on chemical rockets, technology that has remained fundamentally unchanged since the 1960s. These rockets work by expelling mass at high velocity, pushing the spacecraft in the opposite direction. The fastest chemical rockets can achieve speeds of about 25,000 miles per hour relative to Earth. This sounds impressive until you calculate how long it takes to cross interplanetary distances at such speeds. To Mars, 6 months. To Jupiter, years. To the nearest star system, tens of thousands of years. Innovative concepts exist, of course. Nuclear thermal propulsion could potentially cut travel times to Mars by half. Ion drives, which use electricity to accelerate particles to extremely high velocities, offer greater efficiency but minuscule thrust. They work beautifully for robotic probes that can accelerate gradually over months or years, but humans require faster journeys, not just for psychological reasons, but because every day in space exposes travelers to radiation, bone density loss, and muscle atrophy. There is often talk of breakthrough propulsion systems, fusion rockets, antimatter engines, light sails pushed by powerful lasers. These technologies occupy the space between physics and engineering, theoretically possible but practically distant. Some may arrive within decades. Others may remain perpetually on the horizon, waiting for discoveries we have not yet made, materials we have not yet invented, energy sources we cannot yet harness. It is fascinating to look back at the optimism of earlier eras and see how consistently we have underestimated the challenges of space travel. In the 1950s and 60s, Futurists predicted thriving moon bases by the 1980s, Mars colonies by 2000, and routine travel throughout the solar system by now. These were not fringe predictions. They appeared in mainstream publications endorsed by respected scientists and engineers who had just witnessed humanity split the atom and break the sound barrier. What they underestimated was not human ingenuity, but the compounding difficulties of distance, life support, radiation shielding, psychological stress, economic cost, and political will. The Apollo program, our most ambitious space venture, ended not because we lost the ability to reach the moon, but because we lost the motivation to pay for it. The same rocket equation that limits our spacecraft also limits our budgets. Everything that goes into space is expensive. Everything that keeps humans alive in space is more expensive still. Even within our own solar system, the concept of migration encounters mathematical walls. Consider what it would take to move not a handful of explorers, but thousands, then millions of people. Each person requires food, water, air, shelter, medical supplies, tools, and the infrastructure to produce more of all these things upon arrival. Current calculations suggest that establishing a self-sustaining colony of 10,000 people on Mars, the bare minimum for genetic diversity and industrial capability, would require cargo equivalent to tens of thousands of tons. Launching material into space costs, at best, around $1,500 per kilogram with current technology. SpaceX's innovations have brought costs down dramatically, but the fundamental physics remain. Even with revolutionary reductions in launch costs, moving a city's worth of equipment and people represents an expenditure that dwarfs the most expensive projects humanity has ever attempted. The International Space Station cost over $150 billion to build and serves just 6 to 7 people at a time. This is not pessimism, it is accounting. The numbers exist independently of our desires, and they tell us that interplanetary migration, while not impossible, is so far beyond our current capabilities that treating it as a viable backup plan is like treating learning to swim as a backup plan while the ship is sinking. The timeline and the crisis do not align, yet there is something profound in confronting these limitations honestly. Space is vast and indifferent, but it is also beautiful in its enormity. The same physics that makes migration nearly impossible also makes our Earth, with its perfect distance from the Sun, its protective magnetic field, its breathable atmosphere, appear not as a prison to escape, but as a miracle to preserve. Every mile of distance we measure to Mars reminds us of the miles we did not have to travel to find water, oxygen, and a climate that nurtures life. The brutal physics of space travel do not crush human ambition. They focus it. They remind us that some journeys are worth taking for knowledge, for discovery, for the expansion of human experience. But the journey away from Earth in search of survival may be the longest journey of all, one measured not in distance, but in the centuries of development that stand between dream and reality. We speak of other worlds with longing, imagining refuge among distant skies. Yet every planet we know harbors dangers so profound, they rewrite our understanding of what it means to survive. The universe is not hostile by intent. It is simply indifferent. And that indifference, when translated into physical reality, becomes lethal in ways both immediate and invisible. Mars beckons first in our imaginations, a rusty ember glowing in the darkness. It is close enough to see with the naked eye, familiar enough to dream about. Humanity has sent rovers across its surface, captured sunsets that look hauntingly like home. We see dust devils dance across ancient plains and think perhaps, just perhaps, We could walk there someday beneath open sky. But Mars is not waiting to welcome us. It is waiting to destroy us, slowly and methodically, through mechanisms both chemical and cosmic. The soil itself betrays the first danger. Martian regolith, that fine red dust that covers everything, is laced with perchlorates, toxic compounds that would poison any attempt at agriculture. Touch it without protection and it would burn your skin. Breathe it and your lungs would fail. Even processing water from Martian ice requires removing these chemicals first, an industrial operation that must happen continuously, without error, forever. One contaminated water supply, one breach in a sealed habitat, and the poison enters the human system where it disrupts thyroid function and metabolic processes with quiet efficiency. Above the toxic ground, radiation falls like invisible rain. Mars lost its magnetic field billions of years ago when its core cooled and solidified. Without this protective shield, cosmic rays and solar particles strike the surface unimpeded. On Earth, our magnetic field deflects this radiation into space. On Mars, it accumulates in your bones, your organs, your DNA. The damage is cumulative and irreversible. Each day on the surface adds to a lifetime dose that increases cancer risk exponentially. There is no safe threshold. There is only exposure, measured in millisieverts, each one a tiny probability of cellular mutation multiplied across trillions of cells. The cold is equally merciless. Martian temperatures average -80 degrees Fahrenheit, but near the poles they plummet to -200 degrees. Even at the equator, where conditions are most favorable, temperatures fluctuate wildly between day and night. Steel becomes brittle in such cold. Rubber shatters. Electronic systems fail. Human flesh exposed for even seconds would suffer immediate frostbite, ice crystals forming in capillaries, cells rupturing from within. Maintaining habitable temperature requires constant energy expenditure in an environment where energy itself must be manufactured from sunlight weak enough that solar panels produce only a fraction of their Earth capability. Yet Mars, for all its dangers, is mild compared to Venus. If Mars whispers threats, Venus screams them. Approaching Venus is to encounter a planetary hell, a world transformed by runaway greenhouse effects into something fundamentally antithetical to life as we understand it. The atmosphere, composed almost entirely of carbon dioxide, presses down with a weight 90 times that of Earth's air pressure. This is not merely uncomfortable, it is crushing. At the surface, the pressure equals that found 3,000 feet beneath Earth's oceans, deep enough to implode most submarines. Temperature completes Venus's apocalyptic portrait. The surface averages 900 degrees Fahrenheit, hot enough to melt lead, hot enough to glow faintly in the darkness. This heat is not the result of proximity to the Sun alone. Venus is actually farther from the Sun than Mercury, yet hotter due to its thick atmospheric blanket that traps heat with perfect efficiency. No cooling system could function in such conditions. No material known could protect human flesh from such temperatures for more than moments. The clouds themselves offer no respite. They are composed of sulfuric acid, droplets that would dissolve exposed skin on contact. These acid clouds drift through an atmosphere moving at hundreds of miles per hour in super-rotating winds that circle the planet faster than the planet itself rotates. To exist on Venus is not to face danger. It is to be instantly annihilated by multiple simultaneous catastrophes of pressure, heat, and corrosion. Even our own moon, Earth's closest celestial companion, harbours quiet hostilities. It appears peaceful in our night sky, a silver disk that has watched over humanity since before we were human. Yet on its surface, the absence of atmosphere creates a vacuum where no sound travels and no breath is possible. Temperature swings are extreme, oscillating between 250 degrees Fahrenheit in sunlight and negative 208 degrees in shadow. There is no gradual twilight, no gentle transition. Step from light to darkness and the temperature plummets in moments. Without an atmosphere to burn them up, micrometeorites strike the lunar surface at thousands of miles per hour. These tiny particles, smaller than grains of sand, carry enough kinetic energy to puncture spacesuits and damage equipment. The constant bombardment over billions of years has pulverized the moon's surface into a fine powder called regolith that clings to everything, works its way into mechanical seals, and irritates lungs if inhaled. The dust particles are jagged, unlike Earth's sands smoothed by wind and water, making them abrasive and potentially carcinogenic. Some speak of exoplanets with hope, worlds orbiting distant stars in what we call habitable zones. These are places where liquid water might theoretically exist, where temperatures might fall within ranges life could tolerate. Yet the distances involved render them effectively unreachable with any technology we possess or can envision developing. The nearest potentially habitable exoplanet lies over 4 light-years away. At the speed of our fastest current spacecraft, the journey would take 70,000 years. Even if we could approach the speed of light, which requires energy beyond our capacity to generate, the journey would still take years of ship time and centuries of Earth time due to relativistic effects. And when we arrived, what would we find? Almost certainly not paradise. Each exoplanet exists within a unique evolutionary context shaped by its star's radiation spectrum, its atmospheric composition, its gravitational field, and countless variables we cannot observe from Earth. The odds that any random planet would be suitable for unmodified human habitation are vanishingly small. More likely, we would encounter toxic atmospheres, incompatible biochemistry, or environmental conditions that make Mars look welcoming by comparison. Here lies the profound truth we must confront. Earth's harshest environments, the places we consider most inhospitable, are paradises compared to anywhere else we know. The frozen wastelands of Antarctica, the scorching Atacama Desert, the crushing depths of ocean trenches, all of these extreme environments still contain breathable air in their vicinity, accessible water, manageable pressures, and radiation protection from our magnetosphere and atmosphere. Even in Antarctica's heart, where temperatures drop to negative 130 degrees Fahrenheit, conditions are more survivable than a temperate day on Mars. We evolved here, not just as a species, but as a lineage stretching back billions of years. Every cell in our bodies is calibrated precisely for Earth's gravity, Earth's atmospheric pressure, Earth's 24-hour day. Our bones are engineered for exactly 1 gram of gravitational force. Our lungs expect air with 21% oxygen at approximately 14.7 pounds per square inch. Our circadian rhythms synchronize to this planet's rotation. Our immune systems developed in concert with Earth's specific microbiome. Our eyes evolved to process the particular wavelengths of light filtered through this atmosphere. This adaptation is not superficial. It is encoded in our DNA across 3 billion base pairs, refined through innumerable generations, tested against every environmental pressure this planet could produce. We are not humans who happen to live on Earth. We are Earth life that happens to be human. Separating us from this planet is not relocation. It is transformation into something that can no longer properly be called human, assuming we survive the attempt at all. The universe is vast and filled with wonders beyond counting, but it is not filled with homes. Only Earth holds that distinction. a single pale blue world wrapped in precisely the conditions that allow our existence. Every other planet, every distant exoworld, every glittering possibility in the night sky offers only variations on the theme of our extinction. We imagine ourselves stepping out onto a new world as though we were simply changing continents. The sky is a different color, the horizon a different shape, but we walk, we breathe, we live much the same. In our stories, the human body quietly adapts, as if it were as versatile as our imagination. But the truth is quieter and far less forgiving. Our bodies are not generic machines. They are earth-made instruments, tuned over millions of years to a single planet's gravity, air, pressure, magnetism, and day-night rhythm. They expect 1G beneath our feet, a thick blanket of atmosphere above our heads, and a gentle, constant tug toward the center of our world. Remove those expectations, and something subtle begins to happen. Not an explosion, not a dramatic failure, a slow unraveling. In microgravity, the human skeleton enters a negotiation it cannot win. On Earth, every step you take is a conversation with gravity. Your bones respond to that constant stress by remaining dense and strong. In orbit, that conversation goes silent. Muscles no longer need to strain to lift you. Bones no longer need to bear your weight. The result is invisible at first. Yet measured carefully, the numbers are stark. Astronauts lose around 1 to 2% of their bone density per month in microgravity, even with daily exercise. In a single long mission, it's as if parts of their skeleton age decades. The calcium once locked safely in bone leaches into the bloodstream, and if not managed, can form kidney stones or strain other systems. We like to imagine that advanced medicine or future technology will simply patch this. Perhaps one day it will, but for now, every journey away from Earth quietly erodes the structure that allows us to stand at all. Muscles follow a similar pattern. On Earth, your legs and back are in constant use, even when you merely stand still. In orbit, up and down lose their meaning. There is no need to push against the floor, no demand for powerful calves or sturdy hips. Without that demand, muscle fibers thin and weaken. This is muscle atrophy, not from disease or neglect, but from the absence of a force we barely think about. Astronauts spend hours each day strapped to treadmills, lifting specially designed resistance devices, fighting to give their bodies a reason to stay strong. Even so, they return to Earth often barely able to walk, their legs trembling under a gravity they once took for granted. Their hearts, too, have changed. In microgravity, blood and fluids shift upward, pooling in the chest and head, relieving the heart of some of its work. Over time, the cardiovascular system deconditions. The pump built to fight 1G simply doesn't need to try as hard. When astronauts come home, they sometimes faint upon standing. Their bodies must relearn how to live in the very gravity they evolved for. These are not catastrophic failures. They are accumulations. Month by month, cell by cell, space quietly negotiates away the resilience of the human form. Inside the body, the immune system also begins to drift from its familiar balance. Studies on the International Space Station have shown changes in white blood cell function, altered inflammation, and even reactivation of dormant viruses like shingles. In isolation, each of these changes might be manageable. Together, they sketch a picture of a body whose defenses are slightly, but persistently, undermined. Then there is the matter of vision, the windows through which we would witness those alien horizons. In microgravity, the upward shift of fluids doesn't just affect the heart, it presses gently, continuously, against the brain and the back of the eyes. Over weeks and months, the shape of the eyeball can change. The optic nerve can swell. This condition, known as spaceflight-associated neuroocular syndrome, has led to permanent vision changes in some astronauts. Imagine building a civilization among the stars, only to discover that the very act of living off-world slowly blurs the sight of its inhabitants. The cost of leaving gravity is not just in fuel and metal. It may be measured in the clarity of human eyes. Beyond these internal shifts, there is a more ancient danger, one that predates life on Earth itself: radiation. Our planet is wrapped in magnetic fields and air that shield us from the full intensity of cosmic rays and solar particles. Step beyond that shield and the universe becomes more direct. On a trip to Mars, or a long stay on its surface with only thin atmosphere and weak magnetic protection, astronauts are exposed to levels of ionizing radiation far above those experienced on Earth. The risks are manifold: increased likelihood of cancer, potential damage to the nervous system, and genetic mutations that may not reveal their full impact for years or even generations. Some particles pass through the body in straight, unforgiving lines, slicing through DNA, leaving behind microscopic scars the cell must somehow repair or endure. We can build walls against some of this: layers of material, water, clever engineering. We can use the bulk of a planet or a moon as partial shelter. Yet full safety remains an aspiration, not yet a reality. Out there, the universe is not actively hostile. It is simply indifferent, and in that indifference, our fragile biology must fend for itself. Even if we could protect the body, we would still need to understand the mind. Space is not only a physical journey, it is a psychological landscape unlike anything on Earth. Long-duration isolation studies in Antarctic stations, underwater habitats, and simulated Mars bases hint at the toll of distance and confinement. Sleep patterns fray when sunrises and sunsets become irregular or vanish altogether. Small tensions among crew members can grow in the closed loop of a tiny habitat. Feelings of isolation, anxiety, and depression can creep in, not as dramatic breakdowns, but as quiet, persistent weights on the psyche. In orbit today, astronauts are only a radio call and a few hours of flight from home. On Mars, communication delays stretch to tens of minutes. The planet in the sky is no longer a home you can quickly return to, but a memory that grows smaller with each passing day. Our mental health evolved in communities, in open spaces, under skies that cycle from day to night with reassuring regularity. We do not yet know what happens when those rhythms are broken for years at a time. And there is a question more delicate still, one that touches the core of any dream of a backup planet: reproduction. We talk casually about colonies on Mars, of children growing up under alien suns, as if biology will simply comply. Yet we do not truly know whether human embryos can develop normally in partial gravity or in a high radiation environment. Animal studies in space and in simulated low-gravity conditions have shown troubling results: altered development, higher rates of abnormalities, complications in pregnancy. The data is sparse, incomplete, and ethically challenging to expand, but the uncertainty itself is telling. A civilization is not built from a single generation of brave explorers. It is built from children, grandchildren, and the quiet continuity of ordinary lives. If human reproduction falters off-world, if pregnancies fail more often, if development is impaired, if long-term genetic damage accumulates, then the idea of becoming a truly space-dwelling species may meet a biological wall long before it meets a technological one. All of this paints a picture that is easy to overlook, in the glow of concept art and speculative futures. The rarely discussed truth is not that space is impossible for us, but that we may not be biologically suited to live there in the way we imagine. We are not blank slates that can be dropped into any environment. We are finely adapted creatures whose bones, muscles, hearts, eyes, immune systems, and even potential children are all calibrated to a world we already have. None of this means we should not explore. It does not forbid us from building stations, bases, or even long-term outposts beyond Earth. But it suggests that the fantasy of a simple backup planet, a place where humanity can effortlessly transplant itself if Earth becomes difficult, may run up against something deeper than engineering, the quiet, stubborn constraints of human biology. When we float above our world in orbit, we sometimes describe the experience as transcendent. Looking down, Earth appears whole, fragile, and luminous against the black. But inside the spacecraft, something else is happening. The body is counting the days. The skeleton is slowly relinquishing its strength. The heart is relaxing its relentless effort. The immune system is recalibrating to a place it does not fully understand. Space does not kill us in a single blow. It asks for us, slowly, piece by piece. If we choose to go farther, to stay longer, to build something enduring away from this planet, we will have to decide how far we are willing to bend our own biology, through medicine, through technology, perhaps one day through genetic change, to make that possible. Until then, the idea that we can simply move to another world if this one becomes inconvenient is less a plan and more a comforting dream. A dream born on a planet that, for all its storms and scars, remains the only place where the human body is not a slow catastrophe in progress. Imagine, for a moment, that our spacecraft has finally landed, not on a simulated landscape in a training facility, but on real alien soil. The dream has come true. Humanity has its first backup home. Now the clock starts, not in hours or days, but in how long this fragile pocket of life can resist the universe outside. To understand what it would actually take to make that pocket self-sustaining, we have to set aside the poetic images of domes under pink skies and ask a quieter, more difficult question. How many people? How much stuff? For how long? Scientists who study isolated ecosystems and settlement planning often suggest a rough lower bound. Several thousand people at minimum to maintain genetic diversity, social stability, and enough skills to cover the full spectrum of a complex society. Not a handful of pioneers, not a single heroic family under a dome, a small city. Think of everything that exists within a typical city on Earth. Not just the houses, but the web of roles and knowledge. Farmers, engineers, doctors, plumbers, teachers, electricians, mechanics, medics, software developers, machinists. Every one of those roles is attached to tools, and every tool is attached to materials, and every material comes from a chain that reaches far beyond the city limits. Now compress that entire web into a few sealed habitats, on a world that offers almost nothing for free. A self-sustaining colony is not a set of buildings. It is an entire civilization, shrunk down but still somehow complete, missing even a few critical links in the chain, like the ability to make a specific chemical or repair a particular machine, can slowly turn a thriving settlement into a trapped outpost, waiting for a shipment that may never come. This is the resource illusion, the comforting idea that we can simply start over somewhere else with a small collection of brave volunteers and a few cargo holds of supplies. The reality is far less cinematic and far more intricate. Consider food. On Earth, when we say we grow food, we rarely mean we built a closed ecosystem from scratch. We rely on a living planet that has been evolving for billions of years. The soil beneath a field of wheat is not just dirt. It is a city of microbes, fungi, insects, and chemical cycles that quietly transform dead matter into life. On another world, the soil is sterile, or toxic, or frozen. The air is unbreathable. The sunlight is weaker or harsher, or filtered through a thick sky of dust. Agriculture in such a place is less like farming and more like life support engineering. We imagine greenhouses under alien skies, rows of crops glowing beneath artificial lights. But to keep those plants alive, we must become the planet. We must provide every cycle that Earth once handled invisibly for us. Plants need water, light, and nutrients. They also need stable temperatures, pollination, and protection from disease. Every leaf that grows is made from atoms that must be carefully delivered, circulated, and then recovered. If we lose too much nitrogen to a leak or too much carbon to an unexpected chemical reaction, there is no global atmosphere to buffer the mistake. The system doesn't bend, it breaks. On Earth, if one harvest fails, we can import food from somewhere else. On Mars, or the Moon, or a distant moon of Jupiter, there is no somewhere else. The colony is alone with its equations. To truly feed thousands of people indefinitely, we would need vast growing areas, layers of redundancy, and a deep understanding of closed ecological design that we simply do not yet possess. Our current space agriculture experiments are the first hesitant seeds, not the forests of a new world. And food is only one part of the loop. Every breath we take on Earth is borrowed from a planet-scale machine of air and water. The oceans, forests, plankton, soils, and atmosphere form a vast, self-correcting network that keeps oxygen, carbon dioxide, and moisture within narrow ranges that make our existence possible. On a backup planet, there is no such luxury. Water must be captured, stored, purified, and eternally recycled. Every drop that leaves the system, locked in a cracked rock, vented accidentally into space, is lost. A closed-loop water system must be near perfect, not for months, but for centuries. Air is even more unforgiving. Oxygen cannot simply be there. It must be generated and regulated. Carbon dioxide must be removed and either stored or converted. Tiny imbalances, too much humidity, traces of toxins, a slow leak in an out-of-the-way corridor, can accumulate silently until they become a crisis. Our best real-world experiment in this kind of total closure was not on another planet, but in the Arizona desert, Biosphere 2. In the early 1990s, 8 people sealed themselves inside a giant glass and steel structure designed to be a miniature Earth. Rainforests, oceans, farms, even a small savanna. The goal was to see if humans and their life-supporting ecosystems could survive in a sealed world, completely independent of outside inputs. Within months, the balance began to slip. Oxygen levels dropped. Not because of sabotage or some dramatic failure, but because the concrete inside the structure absorbed oxygen and locked it away in chemical reactions. Microbes in the soil respired more than expected, consuming precious O2. The air that was supposed to sustain them became thin. The crew struggled with fatigue and health issues. Eventually, they had to add oxygen from the outside. Certain species died off, others exploded in number. Ants and cockroaches thrived. Some pollinators vanished. Nutrient cycles did not behave as predicted. Despite immense planning, Biosphere 2 revealed how delicately and mysteriously balanced even a small ecosystem can be, and how easily it can drift into unexpected territory. And this was on Earth, under familiar gravity, with access to emergency support just beyond the glass. Imagine performing the same experiment on Mars, with radiation, dust storms, low gravity, and no possibility of a rescue oxygen tank dropped from a truck. Closed-loop systems for air and water do exist in a limited, fragile form on the International Space Station, but they require constant monitoring, maintenance, and the occasional delivery of replacement parts from Earth. They are not fully closed, and they are not permanent. A self-sustaining colony would need to take those early prototypes and expand them into an entire world in miniature, robust, redundant, and capable of running for generations without a single shipment from home. And beyond air, water, and food, there is another layer that we rarely see in the glamorous posters of future colonies: industry. Every habitat, every airlock, every greenhouse frame and circuit board and replacement bolt must come from somewhere. In the first years, it will come from Earth, launch after launch after launch, each one staggeringly expensive. But a true backup civilization cannot live forever on imported spare parts. Eventually, it must dig into the alien ground and build. That means mining local rock and ice, refining metals, producing glass and plastics, manufacturing electronics and tools. It means having machine shops, chemical plants, 3D printers, and the raw inputs they require. It means maintaining the machines that make the machines, in a world where dust creeps into every crack and radiation quietly degrades materials over time. Modern civilization depends on a breathtakingly complex supply chain that spans the entire planet. A single smartphone contains components sourced from dozens of countries and hundreds of factories. A hospital depends on pharmaceuticals, precision instruments, sterilization supplies, and trained staff who, in turn, depend on universities, factories, and energy grids. On another world, the colony must internalize enough of that complexity to be able to stand alone. Not all at once, perhaps, but eventually. And each new capability, making glass, smelting aluminum, producing antibiotics, comes with a long list of prerequisites. You cannot make steel without reliable energy, heat-resistant materials, and mining equipment. You cannot print circuit boards without pure chemicals, complex machinery, and extremely clean environments. You cannot run a hospital without a pharmacy, and you cannot run a pharmacy without a chemical industry. The colony, in other words, must bootstrap an entire industrial ecology from almost nothing. When we imagine a backup planet, we often skip the invisible scaffolding that makes civilization possible. We see the destination, a thriving city beneath a foreign sky. But we rarely trace the line of every bolt, every wire, every dose of medicine, all the way back to where it came from. There is nothing inherently impossible about building such a web beyond Earth. With enough time, energy, and patient engineering, we may learn to grow food in alien regolith, to spin atmosphere from rock and ice, to build factories that hum beneath crimson or golden skies. But when we call this a backup, we risk shrinking the problem into something it is not. We imagine copying a few files to an external drive. In reality, we are talking about recreating, from scratch, the only known self-sustaining biosphere in the universe, using fragments of technology and knowledge, with no safety net. The dream is not wrong. It is simply bigger, heavier, and more fragile than the word backup suggests. And as we turn from resources, we can count tons of steel, liters of water, kilowatts of power, to resources that resist measurement. Another question rises quietly to meet us. Even if we could build such a world, what would it feel like to live inside it, knowing there is no outside to turn to? Long before rockets and radiation belts, Before equations of orbital mechanics or debates about terraforming, there was another kind of journey, the one we took in our stories. Across deserts and oceans, through forests and mountain passes, humans have always told tales of a frontier, a place just beyond the map where the rules might be different, where the past might loosen its grip, where a new beginning might be possible. For some cultures, it was the horizon over the sea. For others, it was the unexplored continent. Today, it is the sky itself. The idea of a backup planet is not only a technical dream, it is a narrative, a continuation of an ancient pattern in the human mind. When Earth feels crowded, fragile, or unstable, the cosmos becomes the last frontier, the final blank page in a story we have been drafting for thousands of years. In this quiet moment between worlds, it is worth pausing to ask, what are we really searching for out there? A second home, or a second chance? Our attraction to frontier narratives runs deep. Psychologists describe a tension within us between stability and novelty. We crave roots, but we also long for edges. The frontier promises both. A distant place where we might carry our familiar values while leaving behind our familiar problems. It is the hope that geography can dissolve history. In older times, this longing played out on maps that could be redrawn. The blank spaces of Earth were invitations to the imagination. Today, most of those spaces are filled in. Satellites trace every coastline, every island. The cartographer's ink has circled the globe, and yet the longing remains. So we lift our eyes upward, and the sky becomes the new unmapped ocean. Mars becomes the new wilderness. Orbital habitats become the new island chains. The story has simply shifted altitude. In this way, the backup planet is more than a plan. It is a myth. Not myth in the sense of falsehood, but in the older sense, a structuring story, a lens through which we understand ourselves. For many people, especially in a secular age, the promise that humanity might continue among the stars functions like a kind of salvation, only without the rituals, without the temples, without the gods. Instead of divine rescue, we imagine technological ascent. Instead of heaven, we picture domes on Mars and cities hanging in the darkness, glowing with artificial sunrise. In this secular mythology, extinction is not the end. It is simply the failure to launch. To be saved is to have a ticket on the next rocket. To be lost is to be left behind on a world that could not be fixed in time. The language we use often mirrors older spiritual traditions. We speak of the destiny of our species, of spreading life through the cosmos, of becoming multiplanetary, as if it were a kind of cosmic baptism that washes away the risks of being bound to one fragile world. The universe becomes a stage on which we hope to transcend our current limitations, our conflicts, our mistakes, and yet, like all myths, this one carries shadows. At the center of the modern backup planet dream stands a particular kind of figure, the visionary technologist. Someone who looks at climate graphs and extinction curves and geopolitical tensions and, instead of despairing, reaches for blueprints. In many ways, this is a beautiful instinct. It is the belief that no problem is beyond comprehension, that with enough data, enough creativity, enough engineering, we can find a path through. This mindset has given us astonishing tools. Telescopes that can see the atmospheres of distant exoplanets, reusable rockets that leap backward onto landing pads, rover wheels tracing dusty lines across alien soil. It is a form of optimism built not on hope alone, but on the confidence that where there is complexity, there is also structure, and where there is structure, there may be a solution. But taken to extremes, problem-solving optimism can become something else. When every challenge is a potential engineering project, there is a temptation to favor the challenges that are grand, novel, and far away, rather than the ones that are immediate, uncomfortable, and close to home. Building habitats on Mars is a tangible, dramatic problem. We can draw the schematics. We can calculate the mass budgets. We can animate the landing sequences. Fixing the social, political, and economic systems that drive environmental damage on Earth is far less cinematic. It resists neat diagrams. It demands negotiation, compromise, and patience across generations. Here, in this gap, a subtle shift can occur. The backup planet stops being only an inspiring long-term goal and starts serving a quieter psychological function. Relief. Relief from the fear that we may not manage to change our behavior in time. Relief from the grief of watching ecosystems falter. Relief from the moral weight of knowing that the crisis is not a meteor from the sky, but a pattern of choices woven into the fabric of daily life. For some advocates, not all, the dream of a second world becomes a way of gently turning away from the pain of the first. Listen closely to certain arguments, and a new tone emerges. It is not just that colonizing other planets would be exciting, or scientifically valuable, or a powerful symbol of cooperation. It is that Earth, they say, is already too far gone, that political systems are too slow, that human nature is too stubborn, that collapse is inevitable, and so the only rational act is to prepare the life raft, not to patch the ship. This is an understandable response to a frightening situation. When the house is on fire, fleeing through the nearest door is instinctive. But when the house is a planet, there is no outside to escape into. Every world we can plausibly reach in the near future is more hostile than the one we are considering leaving behind. Here, cognitive dissonance begins to whisper. On one hand, we accept the physics that make off-world habitats unimaginably difficult. We can recite the problems: radiation, microgravity, closed-loop life support, psychological strain. We know that sustaining a city on Mars would require mastery of ecological engineering, far beyond what we have yet achieved on Earth. On the other hand, some of us confidently believe that creating such cities is more achievable than reorganizing how we generate energy, grow food, or share resources here at home. We trust our ability to build artificial atmospheres in domes, while doubting our ability to stop damaging the real atmosphere wrapped around our world. In the glow of this contradiction, space colonies become both an escape and a reassurance. If the worst happens, we tell ourselves, the story goes on, somewhere else. If we cannot change everything now, perhaps the future will belong to those who left. But the mind is not divided into strict compartments. The belief in a backup can subtly shape our behavior even when we do not consciously intend it. If we feel, deep down, that there will always be another chance, another world, another later, the urgency of here and now can soften, not disappear, but blur at the edges. And yet, this is not the whole story. To reduce the appeal of space solely to escapism would be to overlook something genuine and profound. Standing beneath a clear night sky or watching imagery from a distant probe, many people feel a quiet emotion that is neither denial nor distraction. Wonder. Space is not only a ladder to flee upward, it is a mirror in which we see ourselves at a different scale. When we look at Saturn's rings or Jupiter's storms, we are not planning suburbs. We are remembering that the universe is older, larger, and stranger than any of our conflicts. This remembrance can be humbling. It can also be healing. For some, the dream of walking on Mars is not an attempt to abandon Earth, but to honor it, to extend the reach of a species that grew from this soil, this ocean, this sky. The desire to explore can coexist with the desire to protect. A person can marvel at rockets and also plant trees. A scientist can study icy moons while working to preserve melting glaciers. Our psychological relationship with the backup planet idea is not simple. It is a weave of hope and fear, ambition and anxiety, responsibility and temptation. We carry old frontier myths into a new cosmic context, and in doing so, we risk both inspiring ourselves to greatness and distracting ourselves from the work directly beneath our feet. Somewhere between the fantasy of effortless escape and the cynicism of total despair lies a quieter possibility. That space exploration can remain a source of awe and learning without becoming a subconscious license to neglect our only proven home. As our imaginary spacecraft drifts onward past the gas giants and their storms, we are left with a choice not of destinations, but of stories. Will the narrative of a backup planet encourage us to abandon a struggling world? Or will the perspective of the cosmos deepen our commitment to it? In the silence between stars, the answer is not written. We will have to write it ourselves. We drift now, not between planets, but between ideas. The engines are quiet. The stars outside the window hold their patient positions. Yet inside the cabin of human imagination, something turbulent begins to stir. It is not made of gas or ice or stone, but of assumptions, of stories we tell ourselves about risk, responsibility, and escape. Economists have a phrase for this: moral hazard. It sounds technical, sterile, almost harmless. But beneath those two words is a pattern as old as civilization. Moral hazard is what happens when someone is shielded from the consequences of their actions, and because of that shield, they become more willing to take dangerous risks. When a company knows it will be bailed out, it may gamble more boldly. When an individual knows someone else will pay for the damage, they may act less carefully. Protection, if misused, becomes permission. Now stretch that idea from bank accounts to biospheres, from insurance policies to entire planets. The backup planet fantasy is, at its core, a story of ultimate insurance. If Earth fails, we will simply move. If this world becomes too hot, too unstable, too damaged, another world will be waiting, like a spare room in a cosmic house. And here is where moral hazard quietly enters the airlock. As soon as we believe we have a planetary escape route, even as a distant hypothetical, it begins to reshape our sense of urgency. Not dramatically, not overnight, but slowly, like a tide rising under the floorboards. The worst-case scenario no longer feels like the end. It feels like relocation. Throughout history, escape valves have a way of changing how seriously we treat the systems we depend on. When cities could dump their waste downstream, they did, and rivers turned toxic long before anyone thought to protect them. When forests seemed endless, trees were cut faster than they could ever regrow, because there was always another mountain, another valley, another untouched grove just beyond the horizon. When industries believed the atmosphere was an infinite sink, smoke and chemicals rose without restraint, under the assumption that the sky would simply absorb it all. So long as there was somewhere else to move the problem was allowed to grow. Consider the age of colonial expansion, when elites in overcrowded or polluted cities believed they could always find new lands overseas. There was less motivation to repair the damage at home. Instead, pressure was released outward through migration, extraction, and displacement. The safety valve did not solve the underlying issues. It simply spread them. Even in more recent times, we see softer versions of this pattern. When companies can move factories to regions with weaker environmental regulations, the temptation to delay cleaner technology grows. When waste can be exported, the incentive to reduce it at the source weakens. The existence of an elsewhere becomes a license to postpone responsibility. A backup planet is the largest elsewhere the human mind has ever constructed. The danger is not that engineers and astronauts suddenly wish harm on Earth. It is subtler than that. It is a cultural shift, a quiet reordering of priorities in which the sentence, "We must fix this here," slowly becomes, "We should fix this here." But we also have a plan B. In a world of finite resources, plan B is never neutral. Imagine for a moment the scale of investment required to make another world truly habitable, not for a handful of pioneers, but for meaningful numbers of people. Vast fleets of rockets, self-sustaining life support systems, radiation shielding, enormous underground habitats or domes, terraforming technologies that dwarf anything we have yet built. Every dollar, every hour, every laboratory and launchpad we devote to building permanent self-sufficient colonies elsewhere is $1, an hour, a facility not devoted to stabilizing the climate here, restoring ecosystems here, rethinking energy, agriculture and industry on the only living world we currently know. There is no budget labelled magic money for Mars that does not touch Earth's priorities. The trade-offs may be complex, spread across agencies, companies and nations, but they are real. We already know that we can mobilize extraordinary resources when we choose to. The space race of the 20th century redirected massive economic and scientific energy toward a single overarching goal, reaching the moon. Today, some propose a similar mobilization for Mars or other worlds. But imagine, with the same clarity, what a planetary mobilization to regenerate Earth would look like. Global reforestation on a scale comparable to interplanetary rocket fleets. Cities retrofitted like spacecraft to recycle water, materials, and heat with extraordinary efficiency. Energy systems transformed with the same urgency as a launch window closing. The question is not whether space research is valuable. It clearly is. The question is, what story are we telling with it? If the story is, we explore to understand and to better protect our home, then each mission outward becomes an investment inward. If the story is, we will leave when this place breaks, then the very same technologies begin to tilt us toward abandonment. There is another layer to this hazard, one that is less about physics and more about power. When people imagine backup planets, they often picture them as a human project. Humanity will go. We will colonize. We will survive. But history suggests something different. It is rarely humanity, in the broad sense, that boards the lifeboats first. If a viable off-world habitat ever exists, access will not be evenly distributed. It will be governed by wealth, influence, and politics. Seats on the Ark will be limited, and those most responsible for environmental damage may also be best positioned to escape its consequences. In that scenario, the moral hazard deepens. If the people with the greatest power to change Earth's trajectory also hold golden tickets to another world, what quiet calculations might shift in the background? A policymaker deciding whether to regulate a polluting industry, an investor choosing between green infrastructure and short-term extraction, a government weighing preservation of fragile ecosystems against rapid exploitation of remaining resources. The presence of a personal or class-based exit option can make harsher risks feel more acceptable, not because anyone intends harm, but because their own vulnerability has been reduced. When lifeboats are available, some captains steer more aggressively. Meanwhile, Those left behind, by far the majority, would face a version of the future shaped by decisions they did not make, on a planet gradually treated less like a home and more like a consumable stage in a larger journey. This is not destiny. It is a possibility, one that deserves to be examined before it hardens into reality. Even without functioning colonies, the rhetoric of a backup planet can influence policy. If leaders speak of Mars or other worlds as eventual refugees, it can subtly shift the Overton window of what is considered acceptable here. Geoengineering schemes may be pursued with less caution. Resource frontiers may be pushed further into oceans, forests, and polar regions under the assumption that if things go too far, the most innovative will simply leave. Yet the physics we explored earlier in this journey still stand. There is no easy exit, no mass migration, no quiet overnight relocation of billions of people through the vacuum of space. For almost everyone alive today, and for countless generations to come, Earth is not just home, it is the only option. Recognizing the moral hazard of backup planet thinking does not mean turning away from space. The same technologies that might one day help sustain life on Mars can help us purify water in deserts, grow food in harsh climates, and design cities that waste nothing. The same satellites that guide rockets can track deforestation, monitor ice loss, and help coordinate disaster response. The difference lies in the framing. If space is framed as an escape ladder, we risk loosening our grip on the ledge we stand on. If space is framed as a balcony, a vantage point from which to better see, understand, and care for Earth, then every probe, every telescope, every rover becomes an act of stewardship. We can choose to treat Earth not as a disposable first draft of civilization, but as the final copy, irreplaceable and singular. The one edition printed in the ink of oceans, continents, and breath. Far outside, beyond our window, planets continue on their silent paths, indifferent to our debates. They do not know or care whether we call them backups or frontiers, but within our small capsule of consciousness, these narratives matter. They shape budgets, laws, inventions, and values. As we drift onward through the dark, the question follows us like a faint reflection in the glass. Are we building escape routes from responsibility or tools for deeper responsibility itself? In that distinction lies the true hazard and the possibility of transcending it. As our thoughts drift from the frozen storms of the outer planets back toward the small blue world we left behind, something unexpected becomes clear. For all our dreams of conquering hostile planets, the place we understand best is the one beneath our feet, the place we are already on, the place we have already begun to heal. We often tell stories of collapse, of coral reefs bleaching and forests burning, of species lost and seasons shifting. These stories are real, and they matter. But they are not the only stories. Woven quietly through the noise of crisis are other narratives, easy to miss, yet profound in their implications. Stories where rivers come back to life, where forests return to bare hills, where the sky itself begins to repair. If the fantasy of a backup planet is a story about escape, these are stories about return, about choosing to stay and learning how to mend what we have. Consider, for a moment, the ozone layer, a fragile shield of gas tens of kilometers above our heads, invisible yet essential. It is the reason life on land is possible. The thin veil that filters the sun's ultraviolet radiation and keeps DNA from unraveling under a relentless storm of photons. In the late 20th century, we discovered that this shield was breaking. Chemicals known as chlorofluorocarbons or CFCs, once celebrated for their stability and safety, were drifting upward. In the cold darkness of the stratosphere, they met sunlight and shattered, releasing chlorine atoms that tore holes in ozone itself. Over Antarctica, each spring, a wound opened in the sky. At the time, the problem seemed almost cosmic in scale. A planetary injury caused by invisible molecules spread across every nation, leaking from refrigerators, aerosols, and industrial processes. There was no single switch to flip, no one country to blame, no quick fix. Yet what followed is one of the most quietly astonishing chapters in human history. Scientists noticed the anomaly. They questioned, measured, and argued. Satellites confirmed the damage. Then, in a rare alignment of politics, science, and public awareness, nearly every country on Earth signed a single document, the Montreal Protocol, a global agreement to phase out ozone-destroying chemicals. Rich nations and poor ones, rivals and allies, all acknowledging the same invisible threat. We did not build a shield in orbit. We did not escape to Mars. We simply stopped harming the sky. Decades later, satellites look again. The hole is still there, but it is healing. Slowly, year by year, the ozone layer thickens. If current trends hold, by the middle of this century, much of it will resemble the pre-damaged state. The planet, when given the chance, remembers how to repair itself. The ozone story does not mean all problems are easy. It does not guarantee that every crisis will end as well, but it is proof of something crucial. Global cooperation at planetary scale is not a fantasy. We have already done it once. Beneath that recovering sky, other transformations are unfolding. In the Scottish Highlands, hills that once rang with axes and grazing herds are being allowed to rest. Fences come down. Native trees like Scots pine, birch and rowan sprout in places where, for centuries, there was only grass and heather. With the trees come insects. With insects, birds. With birds, seeds carried further still. What looked like a barren landscape reveals itself as a paused forest, waiting for the cue to return. Across Europe, large predators once hunted nearly to extinction, wolves, lynx, bears, are slowly reclaiming portions of their ancient range. Not everywhere, not without conflict, but enough to show that ecosystems are not static pictures. They are tapestries that can be rewoven if we give them thread and time. In the waters off the coast of the United States, marine protected areas act as underwater sanctuaries. Where fishing is restricted, fish populations rebound. Coral reefs, still under immense stress, show pockets of resilience. In some places, species once considered doomed begin to creep back from the edge. When we remove dams from rivers, water remembers its path. Sediment trapped for decades rushes downstream, rebuilding lost sandbars and wetlands. Salmon feel the change as if sensing a forgotten heartbeat. They return, generation after generation, to spawning grounds reopened by a single act. Letting a river be a river again. These are not miracles, they are choices. Rewilding is not a magic spell. It is the decision to step back in certain places and let natural processes resume their long, intricate dance. What's striking is not that recovery is possible, that much ecology is always known, but that it can be surprisingly rapid once pressure is lifted. In years or decades, not centuries, landscapes and seascapes begin to shift toward life. At the same time, far from forests and rivers, another quiet revolution is unfolding in cities, power grids, and rooftops. Solar panels, once exotic and expensive, now spread across warehouses, homes, and deserts. Wind turbines rise in lines across plains and offshore shallows, their slow-turning blades marking a transition hard to feel day to day, yet enormous in aggregate. The cost of electricity from sunlight and wind has fallen far faster than many early projections suggested. In parts of the world, it is already cheaper to build new renewable power plants than to keep old fossil fuel plants running. Batteries, grid management systems, and smarter appliances follow, not in a single heroic leap, but in thousands of small innovations. Each one imperfect, each one revised, iterated, improved. The change is uneven, and often too slow for the urgency of the climate, yet it is real. In some countries, a majority of new electricity capacity now comes from renewables. Electric vehicles, once rare curiosities, share highways with combustion engines. Cities experiment with green roofs, urban forests, and cooler materials that reflect rather than absorb the sun. This energy transition is not yet complete. It may not be fast enough without deliberate acceleration. But from a physics perspective, it is profoundly mundane, in the best possible way. We are not inventing warp drives. We are rearranging wires, materials, and financial incentives on a planet that already has breathable air, liquid water, and gravity perfectly calibrated to our biology. Compared to terraforming Mars, restoring Earth is almost unimaginably simple. On Mars, every breath would depend on machinery that must never fail. On Earth, oxygen arrives for free, delivered by forests and phytoplankton that ask only for light, water, and a little space. On Mars, temperatures average far below freezing, and liquid water is unstable at the surface. On Earth, water cycles through oceans, clouds, rivers, and soil with no pumps required. On Mars, radiation rains down from space, unfiltered by a thick atmosphere or global magnetic field. On Earth, our planet already wears a magnetic cloak and atmospheric blanket, softening the sun's harshest output before it ever reaches the ground. The engineering challenge of stabilizing Earth's climate, while enormous, exists entirely within a system already compatible with human life. The challenge of making Mars similarly hospitable is orders of magnitude greater, stretched across centuries, if it is possible at all. Even many of the technologies we dream of for distant worlds are already circling back to help this one. Solar panels were refined in part to power satellites, where sunlight is abundant and fuel scarce. Today, they sit quietly on homes and spacecraft alike, bridging orbit and suburb with the same shimmering cells. Closed-loop life support systems, designed to keep astronauts alive in the sealed volume of a space station, have inspired more efficient water filtration and recycling technologies on Earth. Sensors created to monitor the thin, fragile atmosphere around a spacecraft now measure pollution, greenhouse gases, and weather patterns from orbit, giving us a clearer picture of our own planet's health. The same engineering mindset that imagines habitats on the Moon also designs energy-efficient buildings that hold warmth in winter and release heat in summer. The logic is shared. In space, every watt matters. On Earth, it always has as well. If we choose, space exploration can become not an escape plan, but a mirror, a way to see more clearly the extraordinary nature of the vessel we already inhabit. From far away, the Earth is not a globe sitting in emptiness. It is a ship in a dark ocean. A spacecraft with an atmosphere as its hull, ecosystems as its life support, and cultures as its passengers. It travels around the Sun at nearly 30 kilometers per second, spiraling through the galaxy, carrying every story we have ever told. Unlike any starship we build, this one assembled itself. Its systems have run for billions of years before we were here, and, if we are careful, could run for billions more. To think of Earth as a spaceship is not to diminish it, but to reframe our role. We are not stowaways awaiting rescue from some better vessel. We are crew members, newly aware, inheriting a ship already in motion. Our task is not to abandon it for a lifeboat, but to learn how to maintain it, patching hulls of atmosphere, tending engines of climate and ocean, repairing the intricate machinery of forests, rivers, and reefs. We look outward to the gas giants and ice worlds and see alien beauty. We look inward, back home, and see something rarer still. A world that not only sustains life, but can heal when given the chance. A world where the hardest problems are not the laws of physics, but the choices we make together. In the soft glow of distant stars, the most radical idea is not leaving Earth. It is staying and learning patiently how good we can become at fixing the only spaceship we know for certain we can live on. Imagine for a moment that we have gently turned away from the billboard slogans and glossy presentations that promise a backup planet. The rocket exhaust has faded. The crowd has gone home. What remains is the quiet, persistent question that has followed us since we first looked up at the night sky. If not to escape, then why do we go? We drift now in orbit above Earth, our homeworld filling the window like a living mural. From this height, there are no borders, no lines dividing nations, just swirling clouds, deep blue oceans, and the soft browns and greens of continents that have cradled life for billions of years. The idea of leaving forever feels different from up here. Not heroic, not inevitable, just incomplete. Because there is a difference between exploring space, studying space, and trying to abandon the world that made us. Exploration is a question extended outward into the dark. It is the curiosity that sends probes to distant moons and telescopes beyond the atmosphere, not to escape, but to understand. Research is the slow, patient work of turning those questions into knowledge. The orbits measured, the spectra analysed, the faint radio signals translated into maps of invisible cosmic structures. Colonization fantasies are something else. They are not about asking the universe what it is. They are about asking the universe to become a mirror of us, somewhere else. They imagine Mars as a second Earth, the Moon as a new frontier town, distant exoplanets as backup copies of home. Sometimes this is wrapped in the language of survival, sometimes in the language of adventure. But often, beneath the surface, there is a quiet hope. Maybe we will not have to face what we have done here, if we simply go somewhere new. Yet space, in its vastness, offers us another path, a path that is less about escape and more about recognition. Not a replacement Earth, but a deeper understanding of the one we already have. From orbit, Earth appears fragile, but it is also resilient, complex, and intricately balanced. To truly appreciate it, we look outward. We send telescopes like Hubble and James Webb far from the surface, not to turn our backs on Earth, but to see our story in context. When we study exoplanets cloaked in distant starlight, we are, in a way, studying Earth's possible siblings and cousins. Worlds where the chemistry is different, the climates more extreme, the conditions hostile or unexpectedly gentle. Each one is a data point in a grand cosmic experiment. Which ingredients are common? Which are rare? How fragile is the line between a frozen desert and a warm ocean world? When we learn how atmospheres evolve around other stars, we begin to better understand our own. Climate, habitability, extinction, resilience, these are not abstract words. They are questions written in the air we breathe. We send orbiters to Venus and discover a world whose runaway greenhouse effect has turned its surface into a furnace. In the thick, choking atmosphere of Venus, we glimpse a possible future to avoid. We send landers to Mars and see a once wet world scorched and thinned by time, its rivers long gone, its sky rusted. In its dried riverbeds and ancient lakebeds, we see how delicate liquid water can be on a planetary scale. These are not stories of backup homes. They are cautionary tales and comparative diagrams, helping us read Earth's own trajectory with more clarity. And we do much of this without placing human bodies in harm's way. Robotic explorers have become our eyes, hands, and senses stretched across the solar system. The rovers that crawl across Mars do not need air or food. They do not age in the same way we do. Voyager 1 and 2, those silent emissaries launched long before many of us were born, continue to drift through interstellar space, carrying golden records of our existence. New Horizons glides past Pluto, turning a fuzzy point of light into a detailed world with mountains of ice and hazes of nitrogen. These machines do not experience fear, isolation, or the slow unraveling of a body unmoored from gravity. They are not less heroic for it. In a sense, they free us. They allow us to explore dangerous environments while leaving human life safely near the warm center of our experience. Earth. With each robotic mission, the cost is measured not in human suffering, but in engineering, patience, and persistence. The data they send back is a treasure shared by everyone on this planet, whether or not they ever leave the ground. While we dream with these explorers, another kind of space science quietly reshapes our lives here at home. Orbiting above us is a lattice of satellites, invisible to the naked eye, tracing arcs across the sky. They watch the breathing of our planet. They see forests expand and shrink, glaciers retreat, storms gather strength over warm oceans. They track rising sea levels, shifting weather patterns, the faint signatures of pollution dispersed in the air. Through them, we witness Earth not as a static backdrop, but as a living system in motion. Without these orbital sentinels, climate change would be much harder to measure, to understand, to respond to. Our maps of disaster, recovery, and adaptation would be blurry. Our forecasts of storms, floods, droughts, and heat waves would be blind. Communication satellites knit distant communities together. A message that once took weeks to cross an ocean now travels in a fraction of a second, bouncing silently off metal mirrors in the sky. Global positioning satellites guide ships, planes, and rescue teams. Emergency beacons call for help from the far corners of wilderness and sea, and space responds by pinpointing a location on a rotating world. Even technologies born for spaceflight, materials, sensors, medical devices, energy systems, quietly filter back into everyday life. Insulation designed for spacecraft keeps buildings warmer with less energy. Imaging techniques developed for observing distant galaxies help doctors see inside the human body with greater precision. Advanced water purification systems, radiation detectors, solar cells, all carry the fingerprints of space research. In this light, space is not an escape route. It is an extension of our tools for caring for Earth and one another. Beneath all of this lies a deeper motivation, one that runs quieter than fear and more steadily than fantasy: curiosity. Curiosity is not in a hurry. It does not need a countdown clock or a promise of salvation. It simply asks, again and again, what is out there? How does it work? What does it mean that we exist, here, now, in a universe like this? When curiosity guides our journey into space, the tone changes. The question is no longer, where do we go when Earth fails? But what can the universe teach us about how not to fail Earth? We can still dream of habitats on the Moon, science stations on Mars, even distant voyages to the outer planets. But in this vision, those places are not lifeboats. They are laboratories and lookout points, places where a few may briefly stand in alien dust and feel, perhaps more strongly than ever before, how singular Earth is in its warmth and complexity. Space research has already improved life here in ways that rarely make headlines. Monitoring systems that watch for solar storms protect our power grids. Early warning networks for tsunamis and hurricanes rely on satellites that stare constantly at waves and clouds. Precision agriculture uses space-based data to reduce water waste and improve crop yields, helping farmers adapt to changing conditions without exhausting the land. All of this arises from a simple, patient alignment. We look outward, and then we turn what we learn back toward home. A better vision of space exploration does not ask us to choose between the stars and the soil beneath our feet. It invites us to see them as parts of a single story. A story in which a small, fragile species learns to understand its environment, both near and far, and uses that understanding not to run away, but to stay, to care, and to endure. We do not need a backup planet to give our lives meaning. The one we have is already enough to study, to protect, to marvel at. In the quiet hum of a spacecraft, in the silence of a control room deep in the night, in the soft glow of a screen displaying Earth from orbit, a different dream is taking shape. Not of leaving forever, but of knowing more gently, of exploring more wisely, of letting wonder, not fear, be the engine that carries us into the dark and brings us, again and again, back to the light of home. As we drift farther from Saturn, the rings fade into a luminous thread, then into memory. The giant worlds shrink behind us, their familiar storms and halos dissolving into the dark. Out here, beyond the comfort of planets we can name, a new kind of awareness begins to take shape. Distances are no longer measured in miles or months, but in perspective. In the quiet between worlds, we finally have the space to turn around and look back. Suspended in the vastness is a single point of light. At first, it is indistinguishable from the countless stars around it. But as our instruments sharpen and our minds remember, that point of light resolves into something more. A pale, bluish spark. Earth. Astronauts describe this as a kind of awakening, the overview effect. From low Earth orbit, from the moon, from the distant vantage of robotic explorers, they report a deep, almost disorienting realization. The borders we draw are invisible, the conflicts we obsess over microscopic, the entire human story compressed into a faint, glowing crescent, wrapped in thin swirls of cloud. From here, Earth is not a nation, a map, or even just a planet. It is a living surface, breathing oceans and forests into the thin film of atmosphere that holds everything we know. Every language ever spoken, every song ever sung, every memory, every loss, every promise, every dream about backup planets and distant colonies, held inside that fragile glow. The overview effect is more than poetry. It is a shift in identity. Many astronauts come home speaking in new terms, not as representatives of a single country, but as members of a single species, caretakers of a single home. When you've seen how alone Earth really is, the fantasy of an easy escape begins to feel less like a plan and more like a distraction. We are, as far as we currently know, the only place in the universe where life has learned to look back at itself. That may change. Perhaps under Europa's ice, in Enceladus's plumes, in the methane lakes of Titan, or on a planet circling a distant star. There are other stories unfolding. But at this moment, with the data we have, Earth is the only confirmed cradle of life. To be born in such a place is not just luck, it is responsibility. Imagine the solar system as a vast library of stone, ice and gas, moons of glassy frost, planets of burning clouds, asteroids of ancient metal and rock. Page after page of cosmic history, rich with physics, but silent. And then, on one small temperate world, the ink changes. Chemistry crosses a threshold. Molecules assemble into cells, cells into creatures, creatures into minds that can wonder why anything exists at all. We are the one page in this library that knows it is being read. This knowledge carries weight. If Earth is the only known oasis in a desert of vacuum and radiation, then preserving its ability to harbour life may be one of the rarest responsibilities in the cosmos. The Backup Planet story imagines responsibility as something we can outsource, copy, or abandon. But the physics of space, the biology of our bodies, and the limits of our current technology all whisper the same truth. There is no easy second chance. For many indigenous cultures around the world, this truth is not new. Long before rockets and telescopes, long before the word planet took on its modern meaning, peoples from the Arctic to the Amazon, from the Australian deserts to the Pacific Islands, developed cosmologies that wove humans into the fabric of their environment, rather than placing them above it. In some traditions, the land is not a resource, but a relative. Mountains are ancestors. Rivers are living beings. The sky is not an empty roof, but a realm of kinship and story. Responsibility, in these worldviews, is not just a legal or economic concept. It is a relationship. To take more than you give, to treat the land as disposable, is not just unwise. It is a breach of trust with the world that sustains you. Modern science approaches the planet differently. It measures fluxes of carbon, tracks currents of air and water, models climate systems in supercomputers. Yet beneath the equations lies a similar insight. We are not separate from Earth systems. We are participants in them. Every breath connects us to forests and phytoplankton. Every sip of water has cycled through clouds, rivers, and stone. The atmosphere is not out there. It is inside us. When you combine indigenous perspectives on relationship with scientific understanding of interconnected systems, a new kind of cosmic responsibility begins to emerge. It is not about owning the planet. It is about belonging to it. This belongs to our story of space too. To step off the Earth, even in imagination, is to see how interdependent it really is. The thin, shimmering boundary of the atmosphere, the delicate balance of temperature and chemistry that keeps water liquid and ecosystems alive. The narrow band of conditions in which a complex, technological civilization can flourish. Out here, in the blackness between planets, that balance looks less like a backdrop and more like a miracle. The philosophical weight of our situation is profound. We live at the intersection of two extremes: incredible rarity and incredible fragility. The universe is vast, but the spaces where life can persist are narrow, like threads of warmth woven through a tapestry of cold. Our biosphere has survived asteroid strikes, ice ages, and mass extinctions, yet it is still vulnerable to our own choices and to chance. Knowing this could paralyze us. It could tempt us toward fatalism or a desperate race to escape. But there is another way to respond. Instead of searching for meaning in the promise of elsewhere, we can find it in the commitment to here. A mature civilization might not be defined by how far it can run, but by how well it can stay. Staying does not mean stagnation. It means learning the deep craft of living within planetary limits. navigating change without shattering the systems that sustain us. It means recognizing that resilience does not come from a distant backup world, but from the health of the forests, soils, oceans, and communities we already depend on. There is a quiet courage in this kind of commitment. It is less dramatic than visions of terraforming Mars or seeding the galaxy, but it may be far more difficult. It asks us to grow not just in technology, but in wisdom. Falling in love with the planet we already have is not sentimental, it is strategic. The more closely we study Earth, the more extraordinary it appears. A world with liquid water on its surface, stable over billions of years. A self-regulating climate shaped by life itself. A protective magnetic shield generated by a molten core. A moon that tugs the oceans, stirring tides and rhythms that living things have woven into their cycles. Other planets are beautiful, mysterious, and worth exploring. But they are not replacements. Not yet. Perhaps not ever in the way our fantasies suggest. Yet we do not need to extinguish wonder to accept this. Space remains a place of profound curiosity, of discovery that can reshape our understanding of reality. We can still send probes to Europa's icy ocean, rovers to Mars' ancient riverbeds, telescopes to catch the faint breath of exoplanet atmospheres. We can still dream of walking under alien skies, of listening for distant signals in the cosmic noise. The difference is where we locate our hope. Instead of framing space as an escape hatch from a failing world, we can see it as a mirror that reveals how precious our current world is. Instead of imagining new planets to use, we can imagine new ways to care for the one that already holds us. The stars can inspire us without inviting us to abandon our responsibilities. As our spacecraft continues outward, Earth grows smaller in the window, yet larger in significance. The further we travel, the clearer it becomes. In all this darkness, that faint blue glow is not just another object in the sky. It is the context for everything we are. In the stillness of the journey, we are left with a simple, quiet realization. Our cosmic responsibility is not to flee this place in search of a perfect elsewhere. It is to learn, with all the tools and wisdom we can gather, how to let life flourish here. To be, in the language of both science and story, good ancestors. We can explore the universe with open eyes and open instruments. We can map its storms and measure its distances. But when we ask where our greatest duty lies, the answer keeps pointing back to that small, shimmering world behind us. Home. Our journey began with an alluring idea that somewhere out there, beyond the storms of Jupiter and the rings of Saturn, beyond the silent deserts of Mars and the frozen shadows of distant moons, there might be a second chance for us. A backup, a cosmic escape hatch. We have followed that dream outward, step by step, through radiation belts and vacuum, through fragile bodies and unforgiving distances. Along the way, the fantasy of an easy refuge has slowly melted into something quieter, but more enduring. A deeper appreciation for the one world that already fits us like a second skin. Because after all the numbers, after all the harsh details of surviving on other planets, one truth keeps surfacing like a familiar shoreline. Earth is not just our first home, it is our best one. The idea of leaving it all behind carries a certain romance. It speaks to our curiosity, our restlessness, our desire to outgrow every boundary. When we imagine domes on Mars or cities in orbit, we are also imagining the best version of ourselves, clever, resilient, unafraid. There is nothing wrong with that dream. But tonight, as you lie here listening, we can let that dream soften, not as an escape, but as an inspiration. Not a plan to abandon Earth, but a reminder of what we are capable of when we care enough to build, to adapt, and to protect. All of the technologies we would need to survive on another world, recycling every drop of water, growing food in harsh conditions, capturing and storing energy with exquisite efficiency, are exactly the skills that can heal this one. The tools for a far-off refuge turn out to be the same tools that make home more livable. The difference is not in the science, it is in the choice. We have crossed, in imagination, the depths of the solar system. We have looked down on storms older than our countries. We have seen rings of ice thin as a whisper and mountains of rock drifting in endless night. Out there, beauty is abundant. But safety is not. Here, the situation is reversed. On Earth, the sky is thick enough to breathe. The oceans cradle life in uncountable forms. Soil, only a few inches deep in many places, supports forests that knit the atmosphere together for every one of us. Even the simplest things, the weight of gravity that matches our bones, the pressure that holds our cells in balance, the temperature range where liquid water can linger, are exquisite, improbable gifts. You are lying on a planet that fits you so well you rarely notice it. The air moving in and out of your lungs right now has been through leaves and oceans and ancient storms. The warmth around you has been filtered through a layer of atmosphere that softens deadly radiation into gentle daylight. The sound of this video travels through a world dense enough to carry waves, yet delicate enough for birds to glide and clouds to form. We don't need to make Earth into a spaceship. It already is one, quietly carrying us through the dark at 30 kilometers per second, wrapped in magnetic fields, protected by layers of air and life and time. As you drift towards sleep, you might imagine looking back at our planet from far away, not as a backup to be replaced, but as a singular, irreplaceable oasis, a blue and white pulse of life in a sea of silence. The question is no longer, where do we run if we break it? The question becomes, what can we do here and now to deserve such a home? If you'd like, you can carry that thought gently into your dreams, that your ordinary life, your choices, your care for others and for this world are part of a much larger story. A species that chose to turn its cosmic ambition inward, to restore what it had almost forgotten to love. Thank you for journeying through this exploration with me tonight, all the way from distant worlds back to the ground beneath your own bed. If this helped you relax, or gave you something to ponder as you fall asleep, you're warmly invited to support the channel in simple ways. You can like this video, subscribe, and let us know in the comments where in the world you're listening from right now. It's a quiet kind of map we're drawing together, one made of humans, not star systems. And for those who feel called to go a little further, there is an optional YouTube membership, a way to help us continue making calm, thoughtful science journeys like this one. It's never expected, always appreciated, and entirely up to you. For now, let the idea of backup planets fade into the background. You are already on the world you were made for. Breathe in the air that belongs to you. Feel the pull of the gravity that holds you gently in place. And as the night deepens, let yourself come home, to Earth and to rest.